Okay, good afternoon, everyone. Welcome to the Virtual Lab Forum for the month of April. This is Steve Smith. I'm Director of the Virtual Lab and your host. I'm joined by John Chattel, the Technical Production Manager of the VLab Forum, Logistics and every all-around great guy. We're coming to you live from the VLab studios in beautiful downtown Silver Spring, Maryland. Today we have a very timely topic. We have heard on the VLab Forum already about the National Blend of Models project from the project manager standpoint, and following that we had requests to hear more about the science behind the blend, and so that's what we're going to hear about from Bruce Veenhuis of the Meteorological Development Lab of the Office of Science and Technology in Fusion. So per usual, we will have Bruce present about 30 minutes worth of content and follow that up with question and answers. This reminder that this is being recorded, so immediately following this, the hour-long session, we will upload the recording up to the VLab Forum website that you can look at in your leisure or share with your friends and colleagues. So without further ado, I'd like to introduce Bruce Veenhuis, and the topic for today is the science behind the National Blend of Models temperature elements. Take it away, Bruce.
Thank you, Steve. Before I get started, I'd just like to acknowledge some of my collaborators here at MDL, Tabitha Hunteman, David Rudak, Daniel Plum, David Strom, Jeff Wagner, Christina Finan, and John Wagner. Just thanks to these folks who are also working on this project. So first, I'd just like to give folks a broad overview of the National Blend of Models project. This slide was actually taken from an earlier presentation given by Kathy Gilbert, who gave just a general overview of the National Blend of Models. So just to sort of repeat some of that information here, our objective is to improve the quality and consistency of the NWS National Digital Forecast database. Some of the specific goals of this project are, through an integrated and structured approach, develop a set of foundational gridded guidance products for the NDFD weather elements based on NWS and non-NWS model information. We'd like to create a methodology for a national blend from multiple models, and our initial focus will be on days 3 to 8, but this will be extensible to a full set of deterministic and probabilistic products covering days 1 through 10. Some of our specific requirements include creating an NWS enterprise solution. We also have to meet R2O criteria, and of course there should be no degradation of service. Before I get into the details of how the prototype blend is being created, I'd first just like to acknowledge that there is a lot of other work has been done within the Weather Service to create blended guidance. And I just wanted to give folks a sense of how the MDL blend compares to some of the blends that are being used by the Weather Service. So the blending technique that I'm presenting today uses statistically derived weights based on recent verification. To compare that with a few other blending techniques, so WPC also creates blended guidance, and their system uses expert weights that have been determined by long-term verification, and forecasters often use these weights as a starting point and have the opportunity to adjust the weights based on the synoptic situation. The Central Region also creates a super blend, and as I understand it, that blend is created using expert weights, and here the forecasters have a choice of which models they wish to use in the blend. So I would say the blend we are creating here at MDL is sort of in the same spirit as some of the other blends being created in the Weather Service. There will be 3 main parts to my talk. First, I will just give an explanation of what is currently running with the blend prototype, and I'll try to get down into some of the details and explain how we are actually creating this blend. In part 2, I will provide some scientific reasoning for why we created the blend the way we did. And then finally, I will show some verification results for the blend prototype. Again, just to repeat, the National Blended Models combines forecasts from numerical weather prediction models to produce bias-corrected and statistically downscaled guidance on the 2.5 kilometer NDFD grid. In this talk, I will outline the methodology we are using for 2-meter temperature, 2-meter dew point, daytime maximum temperature, and nighttime minimum temperature. And just at a very high level, each input is being bias-corrected relative to a common high-resolution analysis. And then those bias-corrected components are blended using an MAE-based weighting technique. And here is just an example of what a blend forecast looks like from the MDL, from the National Blend Models prototype. And this is just an example for 2-meter temperature. This is from the 0Z run on April 9th, 2015, and this is a 24-hour forecast. Here is a flow chart depicting the blend. This is how we create the blend. If you look at the top level, you will see the blend inputs. These are the inputs we are using for the blend, and this includes gridded MOS guidance from the GFS, the ECMWF, the NAICE, and the ECMWF ensemble. We are also using direct metal output from the GFS, the GEFS, and the CMCE, and we are working to add direct metal output from the European model as well. On the second tier, this depicts how we actually train the blend. So if you look on the left, we are using the unrestricted mesoscale analysis at the 2.5 kilometer resolution over the CONUS as the analysis of record for training the blend. And we use the IRMA to bias correct each component to the blend and also estimate the mean absolute error of each component. And as you see on the right, we maintain a set of biases and mean absolute errors. On the bottom tier, when we actually go to create a blend forecast, we take the latest gridded MOS and direct metal output inputs. We bias correct those relative to the IRMA analysis and then create an MAE weighted consensus forecast from those bias corrected components. So I'll go into a little bit more detail of how we actually do the bias correction. So we track the bias of each model using a so-called exponentially weighted moving average algorithm, or EWMA. And this is a technique with a long history used in many different fields, not just meteorology. This technique is also sometimes referred to as a decaying average. And I'd like to mention that this is the same bias correction technique that's being used by EMC to bias correct and statistically downscale their models. So if we look at the equation here, this is the equation we use. This is how we track the bias for each component of the blend. If you look at the first term on the right-hand side, that B sub t minus 1, that is our previous estimate of the bias, which we wish to update. And you can see that is multiplied by 1 minus alpha. Here, alpha is the so-called decaying weight or discount factor. And what we do is we're using a value of alpha equal to 0.05. So we're effectively giving the previous bias a fairly high weight of around 0.95. And then if you look at the second term on the right-hand side, you'll see this is the forecast times t minus 1 minus the observation at time t minus 1. So what this is, at this step we are verifying a previously made forecast and just computing the error of that forecast. And you can see we give that single error estimate, we give that a small weight, because remember alpha is equal to 0.05. So we combine that single error estimate with our previous estimate of the bias, and over time, we can learn if there's a systematic bias to a particular model. And this bias correction is performed separately for each grid point, projection, and element. And once we compute our bias, we just simply create a bias-corrected forecast by removing the bias from the raw forecast. So we create our bias-corrected forecast, BC forecast sub t. We also track the mean absolute error of each component in the blend. And again, for this work, we use an exponentially weighted moving average algorithm. you'll see the equation here is similar to that we use for bias correction, except now we're dealing with mean absolute errors. The first term on the right-hand side is the mean absolute error that we wish to update, so it's the MAE at times t minus 1. Again, that is multiplied by 1 minus alpha, and alpha, we use an alpha of 0.05, so we're giving our old estimate a high weight. And then on the second term on the right-hand side, this is just the absolute error for a single case that we are now verifying. And so this is the absolute error that remains after the bias correction. So you can see we're using the bias corrected forecast minus the observation. And again, since alpha is equal to 0.05, we give that instantaneous absolute error a small weight, combine that with our previous estimate, and that's how we track the mean absolute error over time. And again, we use separate MAE estimates for each grid point, projection, and element. So now that we have these mean absolute errors, we need a way to turn these MAEs into weights. And to do that, we use a technique proposed by Woodcock and Engels in 2005. And this is the equation we use to actually compute our weights, where Wm is the weight for member 1. That term A sub m is the most recent MAE for member M, and K is the total number of models being blended. So that this equation looks complicated, but if you actually sort of explode it and try plugging in values, the math is actually fairly simple. So let's suppose we had we had 3 models and we wish to blend those models. And let's say we just wanted to find the weight for model 1. So in the numerator would just be 1 over the MAE for model 1, and then in the denominator it would be the sum of all the inverse MAE for all models in our system. So if we actually plug in actual values into this equation, we can see how the math works. So let's suppose the MAE for model 1 was 2, the MAE for model 2 was 3, and the MAE for model 3 was 4. If we plug those values in, we would find that the weight for model 1 is equal to 0.46. And we would just repeat this procedure for the remaining 2 models to find all the weights in our system. So now that we know the weights, we can actually create a blended forecast using these weights. So again, we take the bias-corrected forecast, the bias-corrected forecast for each member, the BC forecast sub m, and we multiply that by the weight for member m. And we simply sum that over all the models in our system to create the blended forecast. And this is an example of the forecast we produce. So this is an example of the blend, again, taken from the 0Z run on April 9th, 2015. This is just showing the 36-hour 2-meter temperature forecast. So there's a lot of advantages to using this MAE-based weighting technique. For one thing, it's a fairly simple technique. It's fairly simple computation. It's fairly straightforward to code and implement. And as I'll show later, it does produce reasonable results, even though it is a fairly simple weighting technique. One thing that's also nice is it's very easy to handle missing model forecasts. If a particular model is not present, you can simply rescale the weights and compute your blend using those rescaled weights. One drawback is it's fairly simple, so it does not account for the error correlation among models. If you're using a more sophisticated technique, you could do this. And my point here being that you may be able to get slightly better scores, slightly lower mean absolute errors using a more complicated technique. But again, that makes it more difficult to implement on a national scale. So now I'd like to change gears a little bit. Now that I've shown you how the blend is being created, I'd like to sort of provide some justification for why we are creating the blend the way we are. Before implementing this blend prototype, we tested various weighting techniques using a station-based data set. The point being to try to get a sense of what techniques might work well on the actual grid. And for this work, we worked with direct model output 2-meter temperature from the ECMWF deterministic model, the GFS, the GEFS, the CMCE, and the NAM for projections less than 84 hours. And again, for this work, the direct model output was just interpolated 2 stations and then bias corrected relative to the station-based observations using that exponentially weighted moving average algorithm. And the results I'm going to show are for the period 1 October 2008 to 30 September 2012. This is a map just showing the stations I used for this work. Again, it's a set of 335 stations. It's a nice set of stations because you can see they're fairly uniformly distributed throughout the CONUS, Alaska, Hawaii, and Puerto Rico. And here so as I mentioned, we tried a variety of weighting techniques. And the point being, we wanted to get a sense of what might work well on the grid itself. So here I'm showing the various techniques we tried. As you go down this list, you're increasing the complexity of the technique you are using. So, the simplest thing you could do is just give each model equal weights. A bit more sophisticated approach would be to use mean absolute error or root mean squared error based weights. And again, that's using the technique proposed by Woodcock and Engel. Another technique we tried is a technique called grid regression, it's a regression-based technique for weighting the weights, which includes an extra term which tries to avoid overfitting your training data. Another more sophisticated approach is a technique called Bayesian model averaging. BMA was first proposed by Adrian Rafferty out at the University of Washington, and we've tried this technique some in-house here, and we have our own variation on the original BMA technique. So for this work, I used a variation of the actual BMA technique. This plot here is showing the mean absolute error for 2-meter temperature at those 335 stations. The projection is on the x-axis. The mean absolute error in degrees Celsius is on the y-axis. And this first result, this is just showing the mean absolute error. If you simply took your raw components and equally weighted them and computed the mean, this is how well you would do. The next level of sophistication is you could actually bias correct those components and then take the equally weighted mean of those bias corrected components. So that's what's shown here. And you can see there's a huge improvement by simply doing the bias correction alone. A more sophisticated way would be to weight the model based on the recent mean absolute error. The results for that technique are shown here. And you can see that this MAE-based weighting technique improves upon the equally weighted bias corrected blend. The improvement is fairly small, perhaps 1 to 4% in terms of improvement, but it is able to improve upon the equally weighted blend. This next, I'm showing the results for the root mean squared error weights, which again, this is fairly similar to the performance similar to the MAE-based weighting technique. The next result is showing the mean absolute error for the ridge regression approach. And you can note that the ridge regression did actually perform a bit better at the earliest projections, but it does add quite a bit of complexity trying to using this technique. Finally, this is the mean absolute error for the UBMA technique. This is a variation of called UBMA. It stands for Updatable Bayesian Model Averaging. It's a variation of the BMA technique that we have developed in-house. And as you can see, it performed about as well as the ridge regression technique, but again, it's a bit more complicated than using MAE-based weights. So based on this work, I found that the MAE-weighted blend performed well for 2-meter temperature, and that increasing the complexity by using a more sophisticated technique yielded diminishing returns. So I thought the MAE-based weighting technique was probably a good way to go for the national blend. And it's a fairly simple technique. It's robust, and it will be straightforward for us to implement operationally. And I think this MAE-based weighting approach can set a competitive benchmark for future improvements. I'd like to get into now I'm getting into the final part of my presentation. And in this part, I'm going to show some actual verification results for the blend. I will show some gridded verification results relative to the RTMA. I'd like to thank Tabitha Hunteman for providing those from the National Blend and Models Verification Team. I'm also going to show some point verification, comparing the blend versus the bias-corrected ECMWF gridded MOS at stations. And I'd like to thank a colleague of mine, David Rudak, for providing those results. And then finally, I'm going to show some examples of what these MAE-based weights actually look like over time at specific points. This plot here is showing the mean absolute error. This is for the month of February. On the x-axis, you have the projection, and then on the y-axis, you have the mean absolute error in degrees Fahrenheit. And a variety of systems are being compared here. The blend is shown in purple or pink. The NDFD guidance is shown in blue. The gridded MOS is shown in black. And then the DNG is shown in orange. One important point I'd like to make about this slide is, since this verification is performed relative to the RTMA, the blend does have an advantage here because you remember the blend is being trained relative to the IRMA, and the IRMA is just a time-like version of the RTMA. So the blend does have an advantage in this comparison. So I wouldn't get too hung up on any differences between points. Rather, I would mainly conclude that the blend is competitive with the other systems being verified and is in the ballpark with the other forms of guidance. This is a similar plot. This time we are looking at dew point temperature. Again, this is for February 2015. On the x-axis, you have the projection. On the y-axis, you have the mean absolute error in degrees Fahrenheit. And again, keep in mind the blend has an advantage here because the blend is being trained relative to the time-like version of the RTMA. And again, I would mainly conclude that the blend is competitive with the other systems being verified. Another question that we asked was, is the blend more skillful than the single best component? So a colleague of mine, David Rudak, compared the blend versus the bias-corrected ECMWF gridded MOS. And for this work, we interpolated the blend forecast to stations and verified the blend relative to the station-based observations. We also interpolated the bias-corrected ECMWF gridded MOS to stations and again verified those forecasts relative to the station observations. The results I'm going to show are just for 2-meter temperature, looking at the period 1 January 2015, 26 March 2015. This plot is showing the mean absolute error. This is at 300 stations over the period 1 January 2015 to 26 March 2015. Again, the projection is on the x-axis. The mean absolute error in degrees Celsius is on the y-axis. And the blend is shown in blue. The bias-corrected ECMWF gridded MOS is shown in red. And you can see the blend did improve upon the bias-corrected ECMWF MOS. The improvement is small, or it's tough at the early projections, but there is some improvement in the later projections past 128 hours. Finally, I'd like to just show some examples of what these weights actually look like. So what this plot here is showing, this is the 120-hour forecast from the blend at Atlanta, Georgia. And on the x-axis, you have it's the day of March 2015. So what we are looking at is just the first 2 weeks of March 2015. So it's a trace over time of the weights for the different components of the blend. Now on the y-axis, you have the actual value of the weights. So you can see at this particular location, the bias-corrected ECMWF gridded MOS and the bias-corrected ECMWF ensemble gridded MOS tended to receive the highest weight. That was followed by the bias-corrected NAICS gridded MOS, the bias-corrected GSS gridded MOS, and then finally the bias-corrected direct model output component. Here's another example. This time we are looking at Albuquerque, New Mexico. Again, this is for the first 2 weeks in March, looking at a trace of the weights over time. At this, if you look at in the later half of this period, at this particular point, the bias-corrected GSS and the bias-corrected NAICS gridded MOS tended to perform best and had the highest weighting. Finally, this is an example for Seattle, Washington. Again, we are looking at the 120-hour 2-meter temperature forecast. And here again, you can see that the bias-corrected GSS MOS and the bias-corrected European MOS received about the same weight over the time period, followed by the bias-corrected NAICS gridded MOS, and then the bias-corrected direct model output components received the least amount of weight. in summary, the blend prototype is being created by weighting the bias-corrected components using an MAE-based weighting scheme. And I've shown that this weighting scheme, MAE-based weighting scheme, is more skillful than an equally weighted blend. Our plan is to use this technique for 2-meter temperature, 2-meter dew point, daytime maximum temperature, and nighttime minimum temperature. Currently, National Blended Models prototype temperature and dew point grids are being produced on the development WCOS platform. We are working to add daytime maximum and nighttime minimum grids. Those should be available soon. And version 1 of the blend is scheduled for operational implementation in December 2015. That will include guidance over the CONUS domain for 2-meter temperature, dew point, daytime maximum temperature, nighttime minimum temperature, apparent temperature, relative humidity, top 12, sky cover, wind speed, and direction.
Very good, Bruce. Thank you very much for a well-organized and well-presented talk. So at this point, we're going to begin question and answers. Per usual, if you're on the GoToMeeting, please raise your hand if you'd like to ask a question, and John Chattel will unmute you, and you can answer your question to Bruce directly. And we'll also entertain questions in the room. I'll remind folks in the room the mics are open, so try to keep quiet. John, do we have any questions?
Yes. Okay, so Drew Groenewald, he says, will the correlation between variables like 2-meter temperature and 2-meter dew point be considered?
Like I say, we do perform consistency checks to ensure that there is consistency in the final blend. For what we have currently running, the weights can actually be different between temperature and dew point, but we do final consistency checks to ensure that the blend is producing physically realistic grids.
He says, I'm also curious about the basis for geographic extent. Some NWS T/P products have extended into Canada to support hydrological modeling capabilities. However, yours does not appear to thought. And then one last thing, I noticed you extended into the waters of the Great Lakes, but not extensively into Canada there, or in other watersheds.
Okay. Yeah, so the images I showed, those are using sort of a smaller domain, but the plan for the blend we implement will be on an expanded CONUS domain, and we are specifically expanding it to cover the Northwest River Forecast Center and try to add in some of the River Forecast Center parts that we are missing along the northern boundary. So, I mean, to address your question, the final blend will be on an expanded domain.
Pat Bowden has a question. Pat, are you online? Can you talk to us?
Yes, I'm here.
Go ahead. We can hear you.
Okay. From what I've seen so far, it looks like the data that's going to be coming into the FOs is going to be in 6-hour increments. And there's concern about that, meaning that we would miss the minimum RH forecasts that generally occur late in the afternoon. Do you think that it's only going to be a 6-hour grid that we get and we interpolate in between, or are we actually going to be able to see 3-hourly forecasts guidance coming in to help us? Otherwise, our fire weather forecasts, we get a lot of feedback from them, and the thing that we mess up the most on is minimum RH. And if we can give them a couple days lead that, hey, it's going to be really dry on a certain day, it'd really make a big difference. And this is one of the drawbacks of the current central region grids that we get, is that there's 6 hours, and we're missing the low RH times in the afternoons.
Okay. Yeah, so the plan for the blend, the projections will match those for NDFD, so there will be 3-hourly resolution data provided. At least matching NDFD, we could possibly go, provide a longer projections than NDFD currently supports. So we are planning to add in 3-hourly temporal resolution to the blend. That is being produced. I don't know, it may not be available yet in any form, but we are producing that.
That answers your
Okay,
question.
so the 3 hourly will go out. Is the 3 hourly going to go out to 72 hours, or what's? I'm not familiar exactly what the numbers are right now.
Well, I know for what's currently running, we're actually producing 3 hourly out to 192. I have to check the exact requirements, but it will at least cover the NDFD. It will at least be consistent with what NDFD provides. We could possibly do, provide more temporal coverage. I mean, we could extend it 3 hourly out past what you can get through NDFD.
Okay.
Is that good?
Thank you.
John,
That's all online for now.
okay, so folks, if you have a question, please use the raise your hand feature in the GoToMeeting or enter a question in the chat box. Do we have any questions in the room?
I have one. For the people online, my name is Jerry Borline. Had a question and a comment. The question is the statistical downscaling. What do you do with that?
Okay. Well, so a couple of things. Jerry asked about statistical downscaling and how we are doing that. The grid and MOS components have already been interpolated to or been analyzed to a 2.5 kilometer grid over the CONUS. But we do bias correct those grids relative to the IRMA to try to handle basically any systematic differences between the IRMA and the grid and MOS. And we also bias correct the direct MOS output fields using the IRMA to try to add in terrain detail.
Okay. The other thing is, I guess I might be intuitively obvious, but I'm looking at a histogram of the forecast before bias correction compared to a histogram afterwards, and that would seem that the histogram after bias correction would be tighter, or you're actually lowering the variance of the distribution.
It may not actually, the spread may be the same if there was a systematic shift one way or another in that histogram, if I understand.
You could do it immediately.
It would, yeah, basically, exactly. That's basically what it's doing.
But I'm thinking it might be artificial, but it's not if it's based on the IRMA. It would be a realistic correction.
Right, and it's sort of tunable based on the choice of the decaying weight you use, how much you are going to adjust each new case that comes in. So what we've done, well, what we're doing is really training on sort of effectively the last 20 or 30 days. So it really takes a systematic shift one way or another to really move the biases much.
I got a question. So you showed a month-long history of the weights for, I think, 2 different locations, Albuquerque and Atlanta, and it looked like they were pretty stable across the month. They were sort of, it was like a different blend at the 2 different locations, but it didn't change much within the month. Is that expected, or was that a surprise, or?
I would say that was expected. Again, we are effectively training on the last 20 or 30 days. So in that kind of time scale, it tends to be sort of consistent. Some models tend to perform consistently better than others. I mean, it's more of a sort of rough long-term. It's not going to say long-term verification, but it's getting more towards like a seasonal time scale of weighting than trying to say jump to different regimes. So it's sort of by design. It's tuned so that the weights are fairly stable over time. But I mean, it's something you can tune based on verification.
But there are, at least from those 2 examples, regional and local variations of what the blend looks like.
Right. Yeah. So the weights can vary geographically. They can vary with element and also projection. So.
Okay. Very good. Thank you, John. Do we have?
No, we have no additional questions.
In the room. All right. I will ask, in terms of, so just distinguishing between the blending and the training, so that how often is the training is done every single run, or?
Right. So the training can actually be a bit decoupled from actually making the forecast. So right now the training is done when the latest IRMA analysis grid arrives. So you can, that's sort of the time where we sort of kick off the job and actually update our biases and MEEs. But I mean, it's robust. If you go a few days without being able to update those for whatever reason, you can still use your older biases and MEEs. They just may be a few days out of date. But again, that's not, since we've sort of tuned it to not be terribly sensitive, missing a day or two here or there in your training is not going to have that large of an effect.
Okay, so is it felt like this responsiveness in the blend is sufficient to meet the needs, or would you think it could be more adaptable or more in tune to more recent trends? I guess the question is this getting enough signal from the most recent model performance, or is it being lost in the too much of?
Right. So you're saying I think we would have to really do a careful verification study and try different decaying weights and to get a real sense of what's optimal. I know NSEP has done, Eugen's group has done a lot of work on that. So that's Eugen Zoo. So that was sort of our starting point based on some of their results. They use a similar algorithm. They found values around 0.05, 0.02. Those work fairly well. So that's something with future work, something we could do.
Very good. John?
No, nothing new.
Could you repeat when you plan to make this operational?
Yeah, December 2015.
So you're going to do more testing between now and then?
Yeah.
Training or whatever?
Well, our focus is more on getting, probably expanding the element list, well, it'll be running experimentally over the summer, so that'll give us more time to evaluate it.
I know you're using the CNWS and Sunday. Are you using the median sample number or all users?
So we use both. The question was about our use of European models. So we use both the deterministic forecast and the mean of the European ensemble. And those components are can have different weights in the blend.
Do you anticipate, what do you anticipate when you start looking at precipitation elements? Or are you already doing that maybe?
Right. So actually it's been, Tom Hamill has been more focused on that from Ezreal. His group has been responsible for developing basically the first precipitation element will be the top 12. So I'm not very familiar with that part of the blend.
It's a different approach.
Yeah, it's a very different approach.
Okay. So maybe we should schedule Dr. Hamill. Okay. And so maybe this question is not that directed to you, Bruce, but on terms of how LAMP would play with this, would LAMP use the blend, or would LAMP be separate from this, or maybe Judy? Thoughts? Update? How do we update the blend, or do we not?
Well, I mean, our initial focus is on days 3 to 8. I think when we move to includes day 1 to 3, when there's more of a focus on days 1 to 3. I mean, I guess first off, let me say we will be providing guidance starting with a 6-hour projection, but the way we have set it up is more of a focus on days 3 to 8. But I think we'll probably want to look at adding other models to the mix once we start dealing with the shorter time ranges.
These models you're using are not hourly models, so it's different than updated hourly. So.
Right. Currently, the blend only runs twice a day. I think we still have to decide exactly when the operational version of the blend is going to run. So that's still something we have to determine.
All right. Any comments or questions online? No? Any in the room? Well,
I guess I would hazard a guess that if you're going to get LAMP into this mix, it would be more a matter of updating lamps with your mill stuff rather than updating the mill with lamps.
So you're saying adjusting lamp based on the blend? Or
If there's going to be any adjustment done, I would imagine it would be in that direction. Because the observation is so important in lamp, you're not going to slow it down.
okay, yeah, good point. There's a very good, dealing with the global ensemble, there's a large time lag between the model, from when the model was initialized and when it actually gets, when we actually get the data. So it can be 6-7 hours.
All right. Well, thank you very much, Bruce. And as is mentioned, this the entire recording will be uploaded to the VLab Forum website shortly after this, and the slides are already there. So if you have any further questions, you can zip an email to Bruce directly. And I'd also mention that coming up in May, May 20th will be our next VLab Forum. We'll have a talk on the NOAA Hydrometeorological Testbed Southeast pilot study. And we're also interested in hearing from you on any topics you would like to see presented in upcoming VLab Forums. So if you have any ideas, please send an email to John Chattel or myself, and we'll try to book the speaker for whatever you're interested in. So thanks, everyone, and have a good rest of your day.